Anyone who can respond? Okay, thank you very much for your update, Shivam. Anyone else who wants to respond if the dataset is ready, or I need to wait for you? Okay, so I cannot see any more responses. So I'll just assume that you people have gathered your data set, and now I'm following the very first step that we are doing from past several days. You just have to upload your data set here. You can use drag and drop option, or you can have the upload button also here. So you can just click on this upload to session storage option here, and it will take you to the folder wherever you have kept your dataset. You can select that folder from your device. And for instance, mine is on the desktop, so I can pick up this station_day is the dataset that we'll be using today. So I'm just opening it here, and it will be ready on your screen. Just follow the same step, upload your dataset and make it available on this left side window. It may take some time because this is a little bit bigger data set. So here you will see the processing. When data set is loading, in this portion, you will see the processing. When this circle completes, then it means your data set is ready now. Just let me know if you all have followed this step and the data set is ready here. Then I'll start writing codes. Thanks for the update, Shivam. Anyone else who wants to respond, or if I need to wait for anybody who is just following the previous step, please let me know in chat box. Okay, I cannot see any more responses, so I'm just following one more step here. We need to load the dataset, and as from the past several days, we are following it. We need to use your pandas library, and I hope now you are familiar with that code. So we just have to import pandas as PD first of all. Then we can take up our data variable with pd.read_csv. And inside this function, we need to put address of your file that you need to load. So we'll just go to this file. We'll click on 3 dots and copy path. This will bring you the path of the data file that you are using, and we will put it inside inverted commas. This format you have to follow as it is, inside inverted comma and within parentheses of your read CSV function. And after this, we can just look after the structure of your data by using data head command, which displays first 5 lines of your data. So this is the current structure of your data set. And I'm sharing this tiny code in your snipper window also. You can find it from there in Day-6 file. So just let me know if you have loaded this data set, then I'll explain what we have in this data. If anybody is stuck anywhere, then also let me know. I just hope that you have obtained your data set here. If anyone interested to update, okay, thanks for the update, Shivam. I hope it is going fine with the remaining candidates also. I humbly request you all, please ask me in the chat if you are stuck anywhere. And even if it is going fine, you can update me in the chat box. So once we have obtained our data set, the first most thing we need to do is observe its pattern. That is always the first task in your data processing. So we just need to identify our objectives from this particular data set. This data set belongs to indoor air pollution, and it is monitored from different cities. If you need original source of this data, you can find it on Kaggle platform. So here I can show you the window. This is the original source of data, air quality data in India. You can see here. And then inside this data, you can see we have observations from several different cities here. And then we have your variables. These are all data files available inside your this particular data set on Kaggle. So out of these, we are using this station day. They are different kinds of measurements. We are using this station day file out of this. And this is a 8.63 MB data set, so good enough. We have 16 columns in this data set. You can find them from here. And then the details about each column, you can also look after here. So here they provide complete information about your data set. And as we can see from the descriptions here, this data set can be used to predict air quality index from your data set. So this air quality index is your target variable now. This is how we observe data set. You will find description about everything on the source of data, or you can define your objective as per your background knowledge about the domain. So here, if we check the information, the last two variable, these two belong to your AQI category. So that means these two represent your target variable right now. And now here comes one interesting task. Based on the discussion that we have done on the second day of this course, we have two types of problem solving approach in your supervised machine learning. We have heard about classification. We have heard about regression analysis. I told you at that time that when your target variable is in the form of continuous variable, then we call it a regression analysis, where we do estimations or predictions about the data set. And this AQI bucket, this shows your categorical information or class-based information. As you can see, these are some categories. We can even increase the count and then observe it more. Like I print first 20 lines of this data so that we can have more precise description of it. So here you can see moderate values, poor values, then we have very poor. So this kind of distribution we have. So this represents your class-based data. So as a conclusion, at the initial stage, we can say that we have two target variables possible out of this single data. One of these, that is your AQI, is your continuous variable that we can use for regression analysis. And this AQI bucket is your class-based variable that we can use for classification analysis. So this is a very good data set that can help you understand two kinds of studies in one go. You can understand two types of model building as well as data processing in one go. So this becomes your structure of data. And now let us observe remaining features here. What we have in these are basically parameters of indoor air pollution or general air pollution. You can find them anywhere. So what we have in this is your PM 2.5, PM 10, these are your dust particles. if we go ahead with the background study, these are basically your dust particles that we can see in the environment, where PM 2.5 shows dust particles with the size less than 2.5 micron. And PM10 shows particles with size less than 10 microns. So these both are dust particles that we can see frequently in our air, in which we breathe, or the air that is in our surrounding environment. Similarly, there are several gaseous components or volatile components as well. So a combination of these we can see, such as your NO2 gas, CO and SO2, etc., ozone, etc., everything is there. So some relevant parameters that can help you to predict this air quality index. Air quality index is basically the overall observation of all these parameters that depict what is the quality of air in your surrounding area. So we just by following the pattern of all these variables, we can predict the scenario of air pollution in a specific area. So the same thing we are doing here. In the beginning, we have two more columns. One is your station ID and second is your date column. So on this station ID column, this is basically about the location. As I have shown you here that we have gathered this from the multiple cities. So they have given them name as station IDs, and there are AP001, 2, 3, these kind of names they have assigned to all locations wherever they have placed their sensors for this measurement. And then we have date on the to show on which date we have observed this particular value. So this is daily analysis they have provided from year 2017 to 2020. So this makes up your entire data set. And now with the initial observation, we can say one thing, that these station ID and date column are currently not relevant to our analysis. Station ID we can drop as it is because we did not have any specific details about the location right now. We just need the information about pollutants. Similarly, this date column is not required because we are building a simple machine learning model. We are not doing time series analysis. If you are doing time series analysis, in that case, you may require date column also. So currently, we can drop these two and we can keep remaining others for our further analysis. This is the first stage of cleaning we are following. So just let me know if you have got the idea about the data set, and then we can start proceeding with the cleaning further. Just give me a quick idea if you understood the structure of data. If I need to explain any part again, please let me know. Anyone who wants to update in the chat. Okay, thanks for the update, Shivam. Anyone else interested to update in chat? If I need to wait more or not. Anyone left behind, then also let me know. I can explain right from the beginning. Okay, fine, no responses. So I think we can go ahead. So I'm starting with data set cleaning now. And as I told you, the first task I'll be doing is to drop two important columns, first of all. These ones basically that we are not going to use for the analysis further. So for this, we are building a model here. A small analysis. We have used this multiple times till now, that how we drop columns. So data.drop statement I'll be using. And inside this, I'll keep number of columns that I want to use for the analysis. For instance, the first I have is I need to use same name. Note that your Python platform is case sensitive. We have to use the same name as we have given that initially. So first is this, and second we have is your date column. And because we have to drop them from the column axis, so that we have to write here axis is equal to 1. So this makes your initial analysis, and then we can have your data.head command to see if the new data set is free from these two columns. So let me first update this one and then I'll share this code. Now you can see these two are dropped from the data and the remaining parts we can see here. So I'm sharing this part also in the snipper window. Just run it and let me know if you have this first stage of cleaning done on your data set. Okay, so I can see one response. Fine. So next to this, we can move ahead with some general descriptions of your dataset that we have done earlier also. For instance, we just need to know general information about your data. So I'll be adding here dataset info, just to know how it is structured and what type of elements we have. And I hope you all know now that info function we can use to get general information about your dataset. So here we can see your range index. This shows number of rows in your dataset, and you can see there is a huge number of entries within this dataset. And as we know, the indexing in Python starts from 0. So that is why this indexing is appearing from 0 to last value is 34. Otherwise, we have it up to 35 because that will be one less than automatically. After this, it says total number of columns are 14 in this data because we have dropped 2 columns. So after this, we are left with the 14 columns. And then we have the hash index for all the column values 0 to 13. Here we can see. Then names of every column we can see here in the list. After this, last one we have is data type. So majority of these, or we can say like all features here are in float. However, one last target, that is your class target, it is in the form of object variable, so that we have already seen. And now this middle one, this shows interesting analysis as we have discussed in the previous datasets also. It shows presence of missing values in your dataset. So currently, if we just look at this, we have 10, 80, 35 entries, but none of these follow the similar count for the entries here. It means all of them have some missing values. And first of all, we need to deal with these missing values. So that will become our first most task. After applying your missing value analysis, let us get exact info about how many missing values we have, because we have just observed that yes, every column has some missing values here. So I'll be updating your another set of code, that is null or isna also, both you know, we can apply both of them. I'll be sharing this one also in the snipper. So here we can see a list of missing values in your dataset for each column. And there is one interesting observation you can see. Both these target columns have same number of missing values. It means we can treat them both in the similar manner. So chances are that they may have missing values in the same set of rows. They may be derived from one to other, so they have similar set of missing values. And in data science, we generally prefer that you do not manipulate your target variables unnecessarily. There are very rare cases when we manipulate your target variable, such as in this case, IAQ bucket you have with object entries. So we can convert them into numerics. That is one kind of manipulation you can do. But otherwise, we do not prefer to load this target variable with any outside variable. So that is why instead of filling these missing values, it is better to drop rows that have missing values in the target variable. For the remaining ones, we can apply other analysis. So for these two, I'll be adding up one sequence here. Drop missing values from AQI bucket or any of these targets. AQI variable. Out of any of these, you can drop, and other one will, I hope, also be clean by this subset cleaning. So for this, what we can do, first I'll be sharing this previous one in the snipper window. You can take it from there. So dropping missing values from the target variable right now, and what I'm doing here is data is equal to data dot. Now, instead of using drop function, I'm using drop now function. Drop function that we use here, it deals with dropping your specific columns. Now we are planning to drop missing values. For that, we have another function, which is drop now. And we have to provide it information about which values or from where we need to drop the values. So I'm just writing here the subset of missing values from, for example, AQI or AQI bucket, any of these you can write, so that both the target variables get clean. So let us see what we get after updating these values. First, I'll be running this, and then I'll be again checking missing values in dataset. See, we have now 0, 0 missing values in both target variables, and even in the previous all features, some level got dropped. Earlier, we were having larger number of missing values. If we just observe this one, we have higher number of missing values. But after dropping some rows from here, we could get cleaner information in previous ones as well. Some values are dropped from the remaining columns as well. So this observation you can make from here, and I'm sharing this code in the snipper for both entries. Just run this and let me know if you are on the same level, and then we can proceed further. Update me in the chat box if you have understood the concept up to this. Otherwise, I'll explain it again. Okay, thanks for the update, Shivam. Anyone else who wants to respond or anything you want me to repeat, please let me know in chat box. So now, when we do your data analysis projects, there are so many decision-making processes in between. Every time you have to make a careful decision that is influenced by some statistical details, some rules in data science, as well as some literature surveys. So currently here we have to deal with the missing values. And as a general rule, we always state that if we have higher number of missing values, like for instance, maybe more than 35% missing values in any column, it is better to drop those rows or those columns that are affected by such missing values. For the less than 35% missing values, we can impute those missing entries with some statistical values, such as mean, median, mode, etc. of that particular variable. So currently you can see a variable distribution of missing values in each one of them. So first, let us see the percentage analysis, if we can calculate that how much percentage of missing values we have in each one of these columns. So I'll be just taking this code here, and here I'll write percentage missing. I'll be calculating from this code itself by applying a simple mathematical formula here divided by length of your total data. This will help you to calculate missing value percentage. And here I can just print these values. A simple mathematical formula I have applied here, and I hope this will be clear to all of you. This sum values that we have just recently obtained divided by multiplied by 100 and divided by total number of entries in your data. So accordingly, we have updated them. So here you can see now we can have 4% missing values in the first one. Similarly, 77% missing values in this xylene column. So what observation you can make from here is, for all these, we can apply statistical imputation because they have limited set of missing values. But this last column, this has huge amount of missing values. Xylene, this has very high amount of missing values. So instead of imputing this, we'll be dropping this column as a general rule that we follow in Python, in data science. A higher number of missing values are better to be dropped instead of to be imputed. If you have understood this idea, I have explained it already, then it is fine. If anyone needs me to explain it again, let me know that why we are dropping this column. I have explained it once, but if anyone needs me to repeat it again, I can do. So I have shared this percentage analysis code also in the snipper window. And based on this now, we can apply your next set here, separate, target, and features. Because what I'm doing here is, or you can say that one more thing I'll be using, drop unwanted column as well, because there is one unwanted column as well. So in the previous analysis also have shown you that we need to separate your target variables as well as features, because we have to apply separate set of operations on the features and the operation on the target will be different. So the same we are trying to do. And another observation that we have made in the beginning, we have two target variables. One we have AQI and other we have is AQI bucket. So you will now create two target variable and one feature set while dropping this xylene value. This is the effort we are putting up here. So what we have to do is, for instance, I'm using X variable to create my features. Here I'll be using again the drop function. And inside this, the columns I'm going to select includes two of your target columns. That includes AQI and AQI bucket. We have to use the same pattern as that of your data sheet. And last one we have is this xylene. This we need to drop because we don't want to fill these missing values since they are very high in number. And these values we are trying to drop from the column axis. So I'm putting here X is equal to 1, the same idea that I discussed earlier. After this, the first target variable I'm creating in Y1. And this, for example, will contain your AQI bucket. And then we have Y2, in which I'll be putting up your second variable, which is AQI. And I can even write here for your knowledge that first one we have is classification variable, and the second one we have is regression variable. These are basically your target variables: classification target variable and regression target variable. So this is your initial distribution we are creating. And even if you want to just see the shape of these all elements, that we can check. So you can check 8702511. This belongs to your feature set, and 1 column we have currently in Y1 and Y2. So I'm sharing this particular code in the snipper window and just execute it and let me know if it is working fine. If I need to explain anything again, then also let me know. Okay, so I got one response, and after this, now we have different types of cleaning tasks to perform here. You can work on these target variables as well as on your feature sets one by one to ensure the step-by-step cleaning process. The first one, let us clean one part we have with the AQI bucket column right now, because this AQI bucket column, as we have seen here, includes your object entries. But we generally need numerical values in the target or in any of your features that you need to put into the machine learning models. To avoid this, what we have to do is we just need to convert this AQI bucket column into number-based entries. And how we can do that? See, there are unlimited ways to do same task in Python. You can have variety of coding options. I'm just using one way out of these. First, I'll be checking. Okay, I'm adding here target encoding task. This I have updated here. And for target encoding, this is with Y1. First, let us see how many different classes we have in this target variable. So for Y1, let us calculate value counts in each class. Here you can see we have moderate, satisfactory, very poor, poor, good, and severe. These are different 6 classes you will find in target variable for classification, and we can call it multi-class target variable. Why multi-class target variable? Because we have here multiple classes to work upon. If you have only 2 classes, for example, only these 2, then we call it binary classification problem. When it is greater than 2, we call it multi-class classification problem. So in this case, we have multi-class classification problem. And there is one more important observation. See this carefully. We have 6 different categories in your target variable, but the entries in each one of them are different. This one has very huge amount. These have very less amount. This kind of distribution in your target variable represents a imbalanced data set. Simple English language, imbalanced data set. Why we call it imbalanced? Because not all the categories have same set of entries. And it is important to provide a specific treatment to these kind of data sets so that we can just convert them into balanced category. However, it is not always necessary. We have different approaches to deal with this. We generally take references from the literature while building such models, that whether on your data set it is better to add new values or not. And in order to deal with these imbalanced data set, you can either follow upsampling approach, you can follow downsampling approach. Listen this very carefully. In case of upsampling, we give priority to the majority samples, and we scale up all the lower values to achieve the same count as that of majority values. I'm repeating it again. In case of upsampling, you consider the majority class and then improve samples in all the minority classes to achieve the same set of numbers in every class. So we need 29417 entries in each class if you apply upsampling. The second case is downsampling. In downsampling, you consider the minority class and you try to drop a set of samples from remaining all so that we get same number of entries in all of these. Downsampling and upsampling. In one case, you are adding some random data into the observations based on the current pattern of your data. And in the second case, you are dropping some existing data entries from the sheet, and then you are getting lesser number of values in the outcome. When we have to use which one, that completely depends on type of objective you have to achieve and type of analysis you are conducting, as well as the domain specific. For instance, when we have medical data set, which is sensitive in nature, we just generally prefer that we follow no augmentation technique. We just use it in original version because that is a sensitive patient data. Similarly, in some other areas, these upsampling or downsampling may be allowed. So here we have simple air quality data, and in this we can also apply upsampling and downsampling approach. In this case, we'll be doing a upsampling approach further. We'll just try to increase all these ranges to the same value so that you can just understand how we can populate existing data set to create new one. So currently the first task I'll be doing here is I'll just encode this target variable. There are so many encoding techniques that you can follow. I'm using here one simplest one with a simple dictionary key pair values. You also have algorithms for this purpose. So what I'm using is I'm using a replace function, and inside this I'm updating my dictionaries. With first entry we have is moderate. Same as this, I'll be updating each one of them one by one to give them numerical values. I'll be changing moderate with 0, then satisfactory I'll be changing with 1. You have to use same format as you have in this. If there are spaces, if there are underscores, you have to follow the same. Next we have this very poor. I'll be replacing this with 2, for example. Then we have class poor. This I'll be replacing with 3. This is simple dictionary key pair values. We have discussed this in the starting sessions. Then we have, for instance, 4, and then we have this severe. So good, severe, we have 6 categories. Okay, it starts from 0, so we can have it up to 5. This sequence I'm updating, and since I need my outputs again in this y1 variable, so here I can write in place is equal to true. This in place is equal to true ensures that all these changes gets applied to the same variable y1 automatically. And after this, we can again check value counts of all categories. We have just replaced these name right now, nothing else we have done. Just object entries we have converted into numerical entries. So you can see these objects now are converted into 0 to 5 values. So let me just share. I think this one I may have shared already. Fine. And this one I'm sharing. The task to encode your data. Just let me know if you all are done up to this. If anyone wants me to repeat any part from the previous, I can do that. Please let me know. Anyone who wants to respond in the chat? Okay, fine. So we don't have any responses further. And we can just start with analysis on your feature variables now. So where we have left it, we just saw some missing values in data, out of which xylene we have already dropped. And for these remaining, now we have to do missing value analysis. So this we can do with imputation techniques. There are a variety of imputation techniques that you can try. In literature, you will find most recommendations for imputing missing values with mean, median, and mode of the feature variable. So note that it will be imputation with the same feature variable values, not with the entire data. It clearly means that when you are imputing missing values in PM 2.5, it will be imputed with mean, median, or mode value of the same PM 2.5. You cannot use mean of any other variable or entire data for this. This will be feature-wise imputation. That is always true in your data science. And second thing that beginners get confused with, which technique to choose for this missing value imputation. So here first I'm adding task, missing value imputation. And in this, I'll be writing here the general recommendations that we have in literature for this. We apply mode-based imputation for categorical variables. When there are missing values in categorical variables, we use mode-based imputations for them. Such as if you have gender information, you have male and female entries in your data set. And when you have to impute any missing values out of that, we will just see which one is the majority rank, such as male or female, which one is majority. That will ultimately turn out to be your mode value. And with that, we'll fill up all the missing entries. So everywhere, wherever you have the missing entries, that will be imputed with male values. Second, we have your median. This is for numerical variables without outliers. If your variable is suffering from outliers, sorry, this will be with outliers, you can apply. And mean, again, for numerical variables without outliers, because your mean values are highly affected by noisy observations. That is why you have to impute with mean only if you don't have any noise in your data variable or any outliers in your data variable. However, otherwise we can go ahead with the median values. So currently, because we are not doing any outlier analysis, considering the time limitation of this study, so we are just using one of the techniques. I'll be using mean-based imputation here. Otherwise, we generally prefer statistical approach for this. So what we can do is, since I have to impute it from all these columns, so instead of imputing them one by one, I'll create one simple for loop here so that it gets done in one go. For I in X dot columns, because there are multiple columns, so I'll be iterating through all those columns, and then Xi, I'll be updating every time with filna value, and that will be your mean of every value that we calculate one after another. So what I'm doing here is x1 dot mean, and with this we'll be making updates every time for your data. Equal to xi values means every column will be updated one after other, and every column we are analyzing one by one with mean values of that particular column only, and we are filling those values. So this simple for loop I'll be executing on all your columns, and ultimately we can check if the missing values from your data set are gone or not. So I can execute the same operation again. Now you can see we have 0 missing values in all columns. So I'm sharing this simple for loop also here. Currently I'm imputing it with mean. You can use the same with the median also by just changing this from mean to median. In that case, it will be replacing all the missing values with the median of that particular value. So I have shared this code in the sniper window. Let me know if we all are clear up to this. If anyone is interested to respond or ask anything, please update me in the chat box. I could see one response. Thanks for the update. Anyone else who is stuck anywhere, need any explanation, please let me know. Okay, thank you for the update, Deep. Anyone else interested to respond If anyone is stuck anywhere, please let me know. I can explain everything again. Okay, so I cannot see any further responses. And next task I can update here is, as I told you that in this particular variable, we can apply upsampling. So let us learn how you can do upsampling. I'm adding that task here. There are multiple methods that you can use for upsampling. One of the techniques I'm applying here is upsampling. Smooth upsampling is a widely used upsampling method in your data science. This will just increase your lower class to the higher class easily. And how we do this is, you first need to get your smooth method, and that is available from IMB Learn library within oversampling module, and we can just import it with this exact name. From IMB Learn library within oversampling module, you will find this smooth method. And first, I'm initializing it with all the default values. I told you several times that when we use this with empty brackets, we do not, it means that we are not passing any parameters to the function, and we are using only the default values, whatever it contains as it is. And in the outcome, it will give you two things, that are your features as well as the target variable after upsampling, because we will be applying this upsampling on both sides. So here I'm just applying my method because I have saved my this in SM. So SM I'm using to fit and resample your X and Y1 variable. Let me just verify if we have Y1 variable. Yes, Y1 contains your classification variable. So the same I'm using here. Writing it, upsampling Y1 or class target variable. This is the task we are doing here, and you can even check the outcomes. Maybe if you want to see your SM underscore Y1 value counts after this, just to see if they are equal now or not. This will be Y1. So I can run this part, and now you can see all these categories have equal number of values. Earlier, we were having different values in each category here, but now we are just getting similar values. This is not about frequency, basically. We are just trying to add more samples in each category that was less than the higher value. So highest we were finding here with this one. So for these all, it will add some random samples inside. We call it data augmentation also. Some random samples inside based on the existing pattern of the data. So it will first observe the pattern for the one category, for the two categories, and all these. And ultimately, it will add some random set of samples to make them equal to this entry. This is what your upsampling process does. So based on this, we are getting output with equal number of samples in each category. So I'm sharing this one in the snipper window also. You can apply this and let me know if it works fine. And if you have got the idea, you can check the value counts after this as well. Let me know when you are done with this, and then I'll start with the next process. Anyone who wants to respond? Any queries, anything you have to ask, please put in chat box. Okay, I'll be waiting, no problem. You can update Deep and let me know if it is working fine. If anyone finds any error in between, then also let me know. You got NaN. Where you are getting this? Is this an error, or where you are getting this NaN? Have you executed this procedure in the beginning? Okay, it's working now. So fine, good. So we have these upsampling outcomes by now, and I hope that everyone else is also on the same level, because I cannot see any other update in the chat. So I'm just assuming that it must be working fine. So after this, the smooth upsampling answer we have received, and then one more task that we can do is, we have done that on the yesterday session also. I explained you that when we have continuous variables in your feature set, we need to normalize them. And the reason for that, I have also explained. If anyone needs me to repeat that, I can do that. But if it is clear, then this is fine. So we have to normalize your input features. That is one important task we need to do. So here I'm writing normalizing, or we can also call it precisely scaling feature variables. This is the task we want to execute here. And while working on this, we have plenty of methods that you can utilize. And currently, one more thing you can observe is, now we have two different set of feature variables. Observe this very carefully. I have modified this for the classification type variable. So now for the classification, we have sm_x1 as your feature variable. However, for your AQI target, we have X as your feature variable. I'm writing here this one precisely so that you do not forget what we are doing. I created one variable X earlier that is now as feature variable for Y2 target, which is your AQI, because I have not modified that for AQI. But we have another variable sm_x, or maybe x1. Yes, x1. This is feature variable for Y1 target, which is your AQI bucket target, because we modified that by using smart upsampling. And similarly, we have Y2. This is your target. We can call it AQI target. And other we have is SM underscore Y1. This is currently your target for AQI bucket. The variable names I have described here for each one of these, whatever we have used, these are current variable names for us, so that you can easily identify and call them wherever required. I'm also sharing this in the snipper window. This is just for the notes. You cannot execute this. This will give you an error. But yes, for the notes, you can keep this part. So after this, now as we are going ahead with the normalization of feature variables, so note this very carefully. We need to normalize two things separately. One is this x1 variable, other is sm underscore x1 variable. And why we are doing this? If you just see the structure of this x head, we have all these numerical variables here. Some of these have very high ranges, some have very low ranges. You can see the range is different, as well as unit of all these variables is different. So as I explained you in previous sessions also, when we have such high ranges along with the low ranges, if we train model with the same data set, chances are that the higher ranges may dominate the lower ones. So it is better to scale down your entire data variable to a lower range, where each one of them can be balanced well and they do not dominate each other. So we'll just try to scale them down. The same you will see with your SMX variable, because they have same structure, just the size is different. So if I run this one also, we will see the similar set of observations. Just the size is different. And if you just need to verify the size also, I can use the shape variable. Both of them currently have different size. This one, the original size that we were having, this one after upsampling, because in case of classification variable, we added some random observations to meet the upsampling condition. So that is why they have different size right now. And now let me start with the first set of scaling, that will be scaling or normalizing your first variable, we can say like classification feature set, which we have represented with SMX1. This we are trying to scale now. And for this, as there are multiple procedures that you can use for the scaling purpose, in Python, you will find plenty of existing functions for this purpose. Most commonly, we use min-max scaler, standard scaler, L1 normalization, L2 normalizations, and many other methods also you will find. The technique, how we choose any one of these, that is also very important. Generally, we prefer your standard scaler method when your feature variables follow Gaussian distribution or normal distribution. So for this, we first create plots of data. We have learned about plots in the previous sessions. You can create histograms, you can create density plots. From there, you can just come to know if your data set follows Gaussian distribution or not. If it follows, we follow standard scaler technique. If it doesn't follow, we can follow min-max scaling technique. And there are some L1, L2 normalizations also. They are also recommended in several cases. Currently, I'm not going in depth with that normalization analysis, but I'm using just one method to help you understand. Yesterday also we have used one. I think yesterday we worked with min-max scaler. So today I'll be using standard scaler so that you can just understand that how we implement both of these. The pattern is very simple. Both of them will follow same pattern. Just the formula, or we can say like the algorithm name, we have to change. So from sklearn pre-processing module, yesterday also we imported it from the same. We have to import now standard scaler. Yesterday we imported min-max scaler. So this thing I have changed now. It was min-max scaler yesterday. Now we have your scalar technique here. So standard scalar, this I'm using here. Then we have the variable. We have initialized your standard scalar method, and now I have the new x norm variable out of this. And what I can do is scalar dot fit underscore transform. And what I have to transform is your sm underscore x1. Since I'm doing this with this feature set, so the same I need to use here. Now, there is one important thing that I need to show you. If you use this standard scalar method directly, it gives you output in the form of an array. This is your array structure. But since we are working on data frames, we need data frame, and data frame appears in this structure that we have just recently seen with the data. These are your data frames, well structured with column headings, rows indexes, everything very precisely we can see. But here we are getting output in the form of arrays, which is not precise in terms of your description of columns. So we can convert this array into a data frame by using a simple approach here. Just this one only I'll modify further. Outside this, I'll apply one function, pd.dataFrame. This will convert your array into data frame. But now there is one more problem. If I run this, see, if I run this, we will get the data frame in the output, but names are not here. Why? Understand this carefully, because I have just converted an array into data frame. Arrays do not contain column names. So it just converted it into data frame, but column names it could not preserve. If you want to preserve column names also, we can make one small addition further. I can just add here columns is equal to, from where we have to take columns, from this sm underscore x1 columns, because I'm updating this with the sm x1 dataset. So from there only we can preserve all column names. So this I'm updating here, and let us see what we get in the output. These are now your updated column lists with normalized dataset. You can see they have very low range now. Earlier we were getting this outcome with high values, such as these ones we were looking after. So these were values with your value 20, like 115, like 109. But now we have them on the lower scale, and you can visualize them here clearly. Lower scale for all these input values. I'm sharing this code in the snipper. You can all execute this one and just let me know if it is working fine with your first feature set. Then we have to use the similar with the second feature set as well. Just update me in the chat box if this is fine up to the level. Let me know if I need to wait for anyone, if I need to explain anything. You can just respond me in the chat box if we are all on the same level. Deep, I am not able to understand what you are telling. Are you getting some error or this is working fine. Value is low means okay, working fine. So, okay, that's great. Thanks for the update. And if you people are doing it side by side, you can give one try to the code also. There will be a very simple implementation. Let me give you one simple task. We can have here one next update I'm making. And now we have to change feature set X that we have for the regression data set. For that, we can work now. And you can use the same code, similar kind of code, but make sure you save it in a different variable, give it a different name, and feature set variable also you have to change. Output variable should be also different. Input variable will be also different depending upon what you want to scale down now. I hope you got the idea what I'm asking. You can give it a try and normalize your X feature set also. I'll be waiting for a while in the chat box for your updated code. Let me know if anyone is trying and I need to wait for their update. If no one is trying, then of course I'll be doing this. No responses. So I can just assume that no one is doing it. So of course I have to do. So I'm just taking this previous code itself and I'll be making a small change in this. For example, I'm giving it another variable name, regression, and this one will be now changed to X. And this one also will be changed to X. So let us see what we get in the output. This is your another variable that we can find. Earlier also we had this with X norm and now we have this with X norm regression variable since this is for the regression analysis. So both of them now we have separated here. After this, we can start building your model. So first I'll be building classification model. In order to build model, what we need, the first thing is your training and testing data set. I explained the significance of this yesterday also. So we are just doing that separation right now. For the classification one, first we'll be doing. So what we have in the classification, first I'm writing the variable names here. This is for your features, and Y1 we have for the target. Let me check once again. I think this will be SM underscore Y1. Yes, this one we have for AQI bucket. So the same variable name we have to use. Otherwise, you will get an error. Make sure whatever is your latest variable, the same you have to use for the update. The previous code also I have shared in the snipper window. Now I have to do separation, and same as yesterday, I can use your simple method here. From model selection module, we can import train test split. This technique we have worked upon yesterday also. And then we can get 4 outcomes from this. First will be your X-train dataset, because we are working on classification. So I'll be writing it XC train, for example, so that we can identify it easily. Then we have XC test dataset. Then we have YC train dataset. Then we have YC test dataset. It gives us 4 outcomes that we have written here. And then we can apply the method. So this is train test split, and we have to apply it on X norm variable, SM underscore Y1 variable. These are your features and target right now, from where we are creating the splitting. Then we have test size. This will be equal to 0.25, because we want to put majority of data into training set and minority into test size. So this will be like 75-25 ratio. 75% will go into training, 25% will go into the testing data set. And ultimately, we have shuffle is equal to true, so that all observations get equal opportunity to shift into training and testing data set. And now we can also look after the shape of this data to ensure if everything is working fine. So this shows your input features, your this must be your input target, and this is your test features, and this is your test target. Using these training and testing, now we can build any kind of model. For example, I start with the simple model that we have built yesterday also, decision tree classifier. For instance, we work on this. And how we do this, we already remember from sklearn.tree, we can import decision tree regressor. Sorry, we need classifier, because we are working on classification right now. So we have to call here classifier. And second thing we need is model evaluation parameters. So from sklearn matrices, we need to import, for example, I call accuracy score, and second I'll be calling confusion matrix. You can have classification report also. There are many other parameters that you can try. I'm using these 2 only. So first we have the CT model. I'm giving it name DCT1. So I first need to initialize my model with all the default parameters. Then I can use DCT1 to fit my training data set. And name of my training data set right now is your XC train and YC train. So the same I have to use here for model fitting. And then we can make predictions from this model. So Y underscore pred I'll be using here. YC underscore pred is the name I'm giving to the variable. And we can use it for dct1.predict. And inside this, we can write this one variable, that is your XC test shape. Test variable, because we'll be testing your model on the feature sets from here. This is now how we build our model. Just 3 lines you need to build your model, and now you can print your results. This thing we have studied yesterday also, so the same pattern I'm using here. Our evaluation matrix here is accuracy score. So the same I'm using, and we have to compare it with YC spread. This is the recent variable, and the other variable that we had is this YC test. We have to compare it with this one. So this is the comparison between your prediction and the existing target. The same we can apply for the second variable also, that is your confusion matrix. So for this, what we can do is I can call this parameter, I can apply this here, and then I can also change confusion matrix. This will be displayed as it is. So let us see what we get with this model. So we can see approximately 81% accuracy with the model, and this is your confusion matrix. Confusion matrix, I hope I have explained earlier also, but if anyone needs explanation again, they can let me know in the chat box. Otherwise, this is your final outcome from the decision tree classifier for the classification model building. Now you can apply any other model also. You can test it with multiple models on the same tone. We just need this X train, Y train, etc., and it will be ready on your system. So I'll be sharing this code in your snipper window. Okay, so before this, I'll be also updating your splitting code. Let me know when this classifier model is ready. Then I'll be building your next model, which is your regression model. If anyone has any doubt anywhere, let me know. I can explain everything again. Any query, any basic or any relevant queries, whatever you need to ask, let me know anytime. Okay, so I can continue. So we are just separating your data set now for the regression model. And for this, what we have here is we need to work on two features. One was your, I think, X norm regression. This was the name I have given to the features. And for the target, in this case, we have Y2 variable. This one represents your target. Let me re-verify. This is your regression feature variable. This the same I have used. And we have also created your AQI target. This is in Y2. So this I have updated here. And now I'll be just using the same set of sequences. And I'll just change the variable names from this. In this, I'll be now using your xnorm underscore regression. And here I'll be using Y2. In this, I'll be writing, for instance, for R. And this one also, I'll keep R. These I'll be also updating with R, so that we can just identify your regression variable separately. Now, these are your outcomes for training and testing dataset in case of regression variable, and the size will be smaller in this case. And the reason we already know, because we have not applied any kind of upsampling in case of regression modeling. Upsampling and downsampling goes with classification only. We don't need that in case of regression. So that is why the count of sample is less in comparison to your this set that we created for the classification. And after this, we can build your model. So I'll be just using the other version of decision tree here. So we call it decision tree regressor now, because we are building a regression model. And the pattern will be almost similar. Whatever we are doing here, the similar pattern we have to follow, but just the name of the model and the parameters will change. Check here what changes I'll be making. First, we have to use regressor. So I'll be changing this to decision tree regression. The same I have to use here also for the initialization. I'm also changing the name of the variable so that we can later on verify it also if we run it again. Your Matrices for model evaluation will also change, because in case of classification, we work on accuracy measures. In case of regression, we work on error margins. So here it will be like mean squared error we can consider. You can consider root mean square error. You can consider mean absolute error, mean absolute percentage error. Everything is there. One another I'm taking is R2 score. Just two I'll be taking here for the evaluation right now. And this one I need to change to the regression parameter. This one also I can update. And this will be your YRC now. So R, and this one also. And the parameter type I have to change here from accuracy score to mean absolute error, and then R2 score. So this must make your model ready for the regression analysis, and I can run this part. And we can see 84% R2 score. MSC value is quite high because we are working on a continuous variable, and MSC is your scale dependent variable. It depends on the scale of the target variable. So accordingly, we can see a high value here. But yes, we can rely on this R2 score. This shows 84%. However, we can improve it further. We can tune the model and we can enhance its outcomes. So if anyone is interested to learn about model tuning also, I can teach them model tuning also. We have some time, but if we are done up to this, then I will just wait for any queries if we have from anyone, and I can share these details also. So the codes for all the recent analysis I have entered in the snippet window. You can run it and just let me know if it is working fine. And if we have any queries, then also let me know. Anything you had to ask from the session or from the previous session, you can ask now. Okay, fine. So I think this must be working with everyone. Let me know if we have anything to discuss, any queries from all the sessions that we have taken up to this, or anything you have to say about whatever we have discussed till now. Please let me know. You can turn on your mic, you can turn on your chat, anything you can use. Students, let me know in the chat if you have to ask anything or no.
Okay, all of you, start your webcam. This is the last session of this particular short-term course. Those who are willing to learn something, they can join me in an offline session in the evening, but online session will not be there. This is the last online session because your interaction is not there. So we have decided that those who want to learn something, they can come to us and we will update your uh, doubts over there. All of you, please start your webcam so that we can take the photograph and you need to present physically in the courtyard today to take one photograph, final photograph. Okay. All of you start your webcam. Okay, all of you, I have taken the photograph. You can leave now. And you need to join for offline session if you want.